On a flat field in Camelot, the King Arthur builds a labyrinth which consists of n walls. Each wall is in the direction of an infinite straight line. Also, no two walls are parallel, and no three walls intersect at the same point. We observe that each side of each wall is painted in a light or a dark color. If two sides of different colors of some two different walls meet at some corner, then this corner is opened up. Hence, we have that two different regions, which were previously confined between the walls, are now merged into one region. For a more abstract explanation, if two lines, which consists of a light and a dark side, intersect, and thus cut the plane into four regions, and their intersection meets at four corners, then the corners, which belong to two different colors, are opened up, which results in two regions merging into one region. The wizard Merlin of the Labyrinth can decide which side of each wall will be colored in a dark or a light color, and thus he can merge or divide regions according to the previously mentioned rules. After Merlin decides which side of each wall is colored dark or light, then Morgana places some knights in the labyrinth. The knights are walking in the labyrinth during their patrol, and at some occasions they will meet each other. The labyrinth needs as many knights as possible to be safe, but it is also known that the knights don't like to meet each other during their patrol. This brings us to the main question in this challenge. We have the following main problem. Let us assume that in the labyrinth, we have n walls. What is the maximum number k of knights, such that no matter what is the shape of the labyrinth, and no matter how Merlin decides to organize the side colors of the walls, in the end of this process, Morgana will be able to put k knights in the labyrinth, such that no two knights will be able to meet each other. That is, each region will contain at most one knight. For finding the solution, let us first be reminded with some facts with regards to the combinatorics of lines in the plane. Suppose that we have n lines such that no two of them are parallel, and no three of them intersect at the same point. First, we want to find the number of intersection points of these lines. We observe that each intersection point is obtained by two lines which intersect. Hence, the number of intersection points is exactly the number of ways to choose two lines from a group of n. That is, this is the binomial coefficient of n by 2. Next, we want to find the number of regions which are generated from these lines on the plane. For this, we will find a recursion formula, Tn, for this number. If n is equal to 1, then obviously we have only two regions, and thus T1 is equal to 2. Now suppose that the number of lines is equal to n-1. Then, after adding one more line, we also add another n additional segments. Each such segment divides a region into two regions, and thus the number of regions is increased by n. Hence, for the recursion formula, we have that Tn is equal to Tn-1 plus n. With the initial condition, we obtain that the solution of this recursion formula is Tn equals to 1 plus the binomial coefficient of n plus 1 by 2. Now we can show that no matter how Merlin chooses the colors of the walls, Morgana can insert at least n plus 1 knights, such that no two knights are at the same region. To show this, before the initial organization of the walls, before Merlin decides on the colors of their sides. We associate the regions between the walls as vertices. Now, let us look at a neighborhood of two lines which intersect. After Merlin chooses the colors of their sides, some two regions are merged into one region. In this case, we connect their corresponding vertices by an edge. Thus, we obtain a graph G of vertices and edges, such that each region corresponds to a connected component of G. Since Morgana inserts a knight at each region, the number of knights that Morgana can insert is exactly the number of connected components of G. Now, we claim that G has at least n+1 connected components. Indeed, as we proved, the initial number of regions is equal to 1 plus the binomial coefficient of n+1 by 2. And this is exactly the number of vertices in our graph. We also showed that the number of intersection points is the binomial coefficient of n by 2. Since each intersection point produces an edge in our graph, the number of edges will be the same. At the start, the number of connected components is equal to the number of vertices, and then, each edge that we add reduces the number of connected components by at most 1. Hence, the number of connected components is at least the number of vertices minus the number of edges, which is n+1. Let us show now that Merlin can paint the walls, so that we will have exactly n+1 regions. This will answer the main question in this challenge, and prove that n+1 is the maximum number k that we are seeking. We start with n unpainted walls, and we assume, without loss of generality, that none of them are completely vertical or horizontal. Then, Merlin paints the east side of each wall in dark, and the west side of each wall in light. After the corresponding corners are opened, we claim that we have exactly n+1 regions. Indeed, first, before the corners are opened, it can be easily observed that we have n+1 regions, which are unbounded to the north. Now, we claim that after the corners are opened, each region will be merged with one of these unbounded north regions. Indeed, let us take some region R, which is bounded to the north. Let us consider the northest corner of the R region, which is the southest corner of some upper region, L. Since the shared corner of the R region and L has two different colors from the sides of these regions, it follows that this corner will open up in the direction from the R region to L, and thus these regions will merge together. Continuing in this process, we can take the next upper region, which again will also be merged together. We can continue until we arrive to an unbounded region to the north, and this in particular will imply that this region will be merged with R. Hence, after the corresponding corners are opened, we will have at most n+1 regions. However, we already showed that the number of regions is at least n+1, and thus, we have exactly n+1 regions. This equivalently means that Morgana can insert exactly n+1 knights in the labyrinth. This proves our main assertion, and thus our proof is finally complete.